Everything is spinning. Right now, Earth turns on its axis once every 24 hours. That's why day follows night. Simple enough, but that's not all. Earth also races around the sun, completing a full orbit every year. The sun itself isn't standing still. It's orbiting the center of our galaxy, taking some 200 million years to complete a single lap. In our galaxy, it's spinning too. Billions of stars, all circling a common center. Look through a telescope at other galaxies. They spin as well, grand spirals twirling across the cosmic stage. Closer to home, the pattern repeats. Hurricanes swirl, tornadoes twist, even the tiniest whirlpool in your bathtub spins. So here's the question that haunts the universe. Why does everything spin? Why is rotation everywhere? Why doesn't motion travel in a straight line? Everything in the universe spins. Look around, and you'll notice patterns of rotation everywhere, from the colossal to the microscopic. Earth rotates once every 24 hours, giving us day and night, a rhythm we take for granted, yet it is just the most familiar example of a universal truth. But this spinning isn't limited to our planet. Earth itself orbits the sun, circling at a speed of 67,000 miles per hour, tracing a cosmic path that balances the sun's gravitational pull. And the sun isn't stationary either. It orbits the center of the Milky Way galaxy, taking around 200 million years to complete one lap. Our galaxy itself is spinning, along with billions of stars, forming majestic spiral arms. Peer through a telescope, and almost all galaxies you observe are spinning disks, their motion reflecting the same physical principles on a far grander scale. This pattern of rotation isn't random. Hurricanes rotate, tornadoes twist violently, even water spiraling down a bathtub drain is following the same basic principle. The universe began with motion. From the moment of the Big Bang, particles were not stationary. Energy became matter, and every particle carried some inherent motion. Nothing in the universe is perfectly still. Temperature differences, explosions, and random disturbances created tiny initial spins, almost imperceptible but real. When clouds of gas collapse under gravity to form stars and planets, these tiny motions are amplified. A cloud that appears to drift slowly in space begins spinning faster as it contracts, just as an ice skater spins faster when pulling in their arms. The conservation of angular momentum ensures that once rotation starts, it cannot easily stop. It is a built-in property of moving matter. Rotation appears everywhere because it is a direct consequence of collapse under gravity. As gas clouds shrink, even the smallest imbalance in motion produces a net spin. This is why every star, planet, and galaxy has rotation. Our sun formed from such a cloud, inheriting its spin. Planets formed within the resulting flattened rotating disk, keeping the direction and motion of the original cloud. Even moons, whether formed in planetary disks or via massive collisions like Earth's moon, carry the same inherited rotation. At every scale, from the spiral of a galaxy to the spin of a hurricane, rotation emerges naturally from the combination of initial motion and gravitational collapse. Spin is unavoidable because the universe started in motion and because the laws of physics preserve that motion. Gravity alone doesn't create chaos, it organizes it. Tiny initial rotations get amplified, creating elegant, stable, circular patterns. The spinning structures we observe, planets orbiting stars, stars orbiting galactic centers, storms forming on rotating planets, are all manifestations of this fundamental principle. Rotation is not just a feature of the cosmos, it is one of its defining rules. From the smallest whirlpool to the largest galaxy, the universe is built to spin. It is a constant, unstoppable, and universal motion that shapes everything around us. Orbits are one of the most elegant demonstrations of physics in action. Everywhere we look in the universe, objects are circling something else. Moons orbit planets, planets orbit stars, stars orbit the centers of galaxies. At first glance, it might seem like they should all eventually crash into one another. After all, gravity constantly pulls objects toward the center of mass. The moon is being pulled toward Earth. Earth is being pulled toward the sun, and the sun is being pulled toward the galactic center. Yet despite this relentless pull, these objects rarely collide. Why? Because they are also moving sideways at just the right speed. Imagine throwing a ball straight up in the air. Gravity pulls it down and it eventually lands back in your hand. Now imagine throwing the ball not straight up, but at an angle fast enough that as it falls, the Earth's surface curves away beneath it. The ball doesn't hit the ground immediately. It starts to follow a curved path. Increase the speed even further, and eventually that curved path matches the Earth's curvature perfectly. The object doesn't fall to the ground. It falls around the Earth. This is the essence of an orbit. Continuous falling where forward motion and gravitational pull are perfectly balanced. The moon's orbit around Earth is a real-world example of this principle. The moon moves sideways at roughly 2,000 miles per hour while constantly being pulled toward Earth's center. The result is a graceful, ongoing circle that has persisted for billions of years. Earth's orbit around the sun works on the same principle, with our planet traveling sideways at 67,000 miles per hour. This sideways motion keeps Earth from spiraling into the sun, while gravity prevents it from flying off into deep space. Every planet in our solar system behaves similarly. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune are all continuously falling around the sun, their orbits dictated by this delicate balance of motion and pull. Orbits are not just about preventing collisions, they are also about stability. In the emptiness of space, there is almost no friction, no air resistance to slow objects down. Once a planet or moon starts orbiting, it can continue indefinitely. The sideways motion that created the orbit is preserved by the conservation of momentum. That is why the moon has been orbiting Earth for over 4 billion years, and why Earth has maintained its orbit around the sun for the same span. Orbits are nature's way of keeping order in the cosmos, turning what could be chaos into predictable, stable paths. Even at smaller scales, the same principles apply. Satellites orbiting Earth, planets forming in protoplanetary disks, and even debris around stars all follow paths determined by this balance of forces. The combination of gravitational pull and sideways motion ensures that objects circle smoothly rather than collide. Without this balance, the universe would be a chaotic mess of collisions. Instead, gravity plus motion produces the elegant, predictable orbits we observe everywhere, from tiny moons to massive galaxies. In short, an orbit is the cosmic dance between falling and moving forward. Gravity sets the rhythm, and sideways motion keeps the performer in the loop, circling gracefully forever. This balance explains why the universe is structured as it is, with stable paths that have persisted for billions of years. One of the most fundamental principles behind the spinning universe is the conservation of angular momentum. Simply put, once an object is rotating, it wants to keep rotating. The faster the mass of that object moves closer to its axis of rotation, the faster it spins. This principle is the reason why small initial motions in collapsing clouds of gas and dust can turn into the rapid spins of stars, planets, and even entire galaxies. Without it, the elegant patterns of rotation we observe throughout the universe would not exist. Consider an ice skater spinning on the ice. With arms stretched wide, the skater rotates slowly. Pulling the arms inward reduces the distance between the mass and the center of rotation. Without applying extra energy, the skater spins faster. This is a direct illustration of angular momentum conservation. The total rotational momentum stays the same, so reducing the radius increases the rotational speed. The same principle applies to the collapse of gas clouds in space. A vast, slowly drifting cloud of hydrogen and helium may appear almost motionless, but as it collapses under gravity, its tiny rotation accelerates dramatically. What was once barely perceptible becomes a significant spin, shaping the future star, planet, or galaxy. This is why spinning disks form everywhere. As a gas cloud contracts, not only does it spin faster, but it also flattens into a disk. Picture throwing pizza dough into the air and spinning it. The dough stretches out, becoming a thin circular disc. Similarly, the gas cloud's rotation spreads material outward in the plane of rotation while compressing it vertically. At the center, gravity pulls gas together, heating it and eventually igniting nuclear fusion to form a star. The star inherits the spin of the collapsing cloud, making it a rotating object from birth. The planets forming around that star also inherit this rotation. As particles within the protostellar disk collide and merge, they retain their sideways motion. Dust grains become pebbles, pebbles become rocks, and rocks become planetesimals. All the while, the net spin of the disk transfers to these growing bodies. As a planet accumulates more mass from the spinning disk, its rotation speeds up in accordance with angular momentum conservation. Once the spin begins, it persists, because space provides almost no friction to slow it down. That is why Earth rotates every 24 hours, Jupiter every 10 hours, and why moons also spin on their axes while orbiting their planets. Angular momentum explains more than just individual stars and planets. It also governs the motion of entire galaxies. The Milky Way, like many spiral galaxies, began as a massive cloud of gas with a tiny rotation. As the cloud collapsed under gravity, the spin increased, flattening it into a rotating disk with stars orbiting the galactic center. The same physics governs galaxies of all sizes. Initial motion, amplified by collapse, becomes the organized rotation we observe today. In short, conservation of angular momentum transforms chaos into order. Tiny random initial motions in the universe are amplified by gravitational collapse, producing the rapid spins of stars, planets, moons, and galaxies. It is a universal law that shapes the structure of the cosmos. Without it, rotating disks would not form, stars would not spin, and planets might never develop stable orbits. Spin is inevitable because once motion starts, physics ensures it continues and often accelerates as mass moves inward. This principle lies at the heart of why the universe spins the way it does. The story of rotation in the universe continues with how stars, planets, and moons inherit their spin from the clouds they form from. Nothing in space exists in isolation. Every star, every planet, every moon is born from a larger, collapsing cloud of gas and dust. These clouds, vast and diffuse, are never perfectly still. Tiny, random motions already exist within them. Some regions drift one way, some another. When gravity begins to pull the cloud inward, these tiny motions are amplified. Even if only a slight net rotation exists, it becomes significant as the cloud collapses. This is how the rotation of a massive, chaotic cloud ultimately determines the motion of the objects it forms. As the cloud contracts under its own gravity, it doesn't just collapse into a ball. Conservation of angular momentum ensures that the rotation speeds up as the cloud shrinks. But there's another effect. The collapsing cloud flattens into a disk. The material spreads outward in the plane of rotation while being compressed vertically. At the center of this disk, density and temperature increase, eventually triggering nuclear fusion, and a star is born. That star automatically spins, inheriting the angular momentum of the cloud from which it formed. Our sun, for instance, formed this way about 4.5 billion years ago, and its spin is a direct inheritance of the rotation of the primordial gas cloud. But the story doesn't end with the star. The surrounding disk, called a protoplanetary disk, contains leftover gas, dust, and rock, all orbiting in the same direction as the central star's spin. Within this disk, particles collide, stick together, and gradually grow from dust grains to pebbles, then to rocks, and eventually to planetesimals. As these planetesimals merge into planets, they carry with them the motion they inherited from the disk. This is why planets in our solar system orbit the sun in the same direction and generally lie within the same plane. The sideways motion wasn't something the planets developed on their own. It was built in from the start, inherited from the original rotating cloud, and reinforced through the disk's structure. Moons, too, inherit their rotation in a similar manner. As large planets grow, they often develop their own mini-disks of material, orbiting the planet just like the protoplanetary disk around the star. Within these smaller disks, collisions and accretions produce moons that orbit the planet in the same direction as the planet spins. Even the moon, though likely formed by a giant impact, follows this principle. When a Mars-sized object collided with early Earth, debris was ejected into orbit. That debris formed a rotating disk around Earth from which the moon coalesced. Its orbit matches Earth's rotation, reflecting the direction of motion in the disk. This inheritance of rotation is universal. Every star, planet, and moon has a history of motion passed down from its parent cloud. It explains why planetary systems are orderly rather than chaotic, why planets orbit in the same direction, and why moons often align with their planet's rotation. The patterns of motion we see today are a direct record of the cloud's initial spin, amplified and preserved through billions of years of gravitational physics. In essence, rotation is not something stars or planets acquire later. It is their birthright. From a tiny drift in a gas cloud to the steady spin of a planet, angular momentum flows from the cosmos to every object unbroken, creating the intricate, harmonious motion that fills the universe. Spin is more than a curious feature of the universe. It is a fundamental organizer, the principle that turns chaos into structure. Without rotation, matter would collapse directly inward under gravity, forming dense, shapeless balls. There would be no flat disks, no planets orbiting stars, no galaxies stretching across the cosmos. Spin prevents total collapse by converting what could be random inward motion into stable, predictable paths. It is the reason the universe has structure, and it underpins everything from the smallest whirlpool to the largest galaxy. The process begins with tiny initial motions in the early universe. Gas clouds, already moving in random directions, start to collapse under their own gravity. The small net rotation of the cloud is amplified as it shrinks due to the conservation of angular momentum. This amplification transforms slow, almost imperceptible motion into rapid spin. As the cloud spins faster, it flattens into a disk. Material is pushed outward in the plane of rotation, while compression occurs perpendicular to that plane. From this spinning disk, stars and planets form. The very shapes of planetary systems, the flat, orderly arrangement of planets orbiting a star in the same direction, are direct consequences of this rotational organization. Rotation also stabilizes orbits. Planets orbiting stars, moons orbiting planets, and stars orbiting galactic centers all maintain their paths for billions of years because their motion and gravitational pull are in balance. Spin ensures that objects don't simply collapse into one another, but instead settle into long-lasting, predictable trajectories. The emptiness of space amplifies this effect. With almost no friction or resistance, motion continues virtually indefinitely. Once a planet or moon starts spinning or orbiting, it retains that motion, becoming part of a cosmic dance that persists across billions of years. On a larger scale, rotation shapes galaxies. The Milky Way and countless other spiral galaxies form from enormous gas clouds with tiny initial spins. As these clouds collapsed, the spin intensified, flattening them into rotating disks of stars. Stars inherited the motion of the collapsing cloud, orbiting the galactic center in organized paths. Even elliptical galaxies, which appear more random, contain stars in orbital motion, all a result of the same fundamental principle. Rotation at this scale organizes vast collections of matter into coherent structures, allowing galaxies to form, evolve, and persist. Even chaotic, high-energy phenomena like hurricanes, tornadoes, and whirlpools follow the same underlying physics. Small disturbances in the motion of air or water become amplified into rapid spins, forming stable rotating systems. The patterns repeat across all scales, showing that spin is a universal organizing principle, not just a quirk of planetary systems or galaxies. In the grandest sense, spin is why the universe has hierarchical structure. Stars form in disks, Planets orbit stars, galaxies spin, and clusters of galaxies exhibit motion dictated by gravity. The universe is not a uniform fog of matter, but a highly organized cosmos. Spin preserves motion, shapes trajectories, and creates order from the chaos of gravitational collapse. Without it, planets would crash into stars, galaxies would lack form, and the cosmic architecture necessary for life and long-term stability would not exist. Spin is the universe's invisible architect. From the smallest whirlpool in your bathtub to the vast spiral arms of a galaxy, rotation organizes matter, stabilizes motion, and enables structure. The cosmos is built on this principle, making spin not just common, but essential, the very mechanism that turns chaos into the ordered universe we inhabit.